Chapter 14, High-Temperature Sterilization. Welcome to our comprehensive study of Chapter 14, focusing on high-temperature sterilization. In the world of sterile processing, this chapter represents the core of our daily operations. While we utilize many methods to render instruments safe for patient use, high-temperature sterilization, specifically steam sterilization, remains the absolute bedrock of the healthcare industry. Let us begin by establishing a clear and non-negotiable definition. Sterilization is the process by which all forms of microbial life are completely destroyed. This includes bacteria, viruses, fungi, and crucially, bacterial spores. This definition allows for no gray area. An item is either sterile or it is not. There is no such thing as partially sterile. This distinguishes sterilization from disinfection, which may kill many pathogenic microorganisms but does not ensure the destruction of the most resistant bacterial spores. In the sterile processing environment, when we speak of high-temperature sterilization, we are primarily discussing steam sterilization. Dry heat is technically a modality of high-temperature sterilization, but its application in modern hospitals is incredibly limited compared to the ubiquity of steam. Steam sterilization is the most commonly used, widely available, and inexpensive method of sterilization in healthcare facilities today. Because of its safety and efficacy, the industry operates under a principle often referred to as the golden rule of sterilization. The rule states that if an item can be steam sterilized, it should be steam sterilized. We only resort to alternative methods, such as ethylene oxide or hydrogen peroxide gas plasma, when the device is heat-sensitive or moisture-sensitive. If a device can withstand the heat, steam is always the first choice. Why is this the case? The prevalence of steam sterilization is driven by several advantages. First, it is non-toxic. Unlike chemical sterilants that may leave harmful residues, steam is simply water vapor. Once the item is cool and dry, it is safe for immediate use on a patient. Second, the cycles are relatively fast, allowing for rapid turnover of surgical instrumentation. Third, it is the most economical option. The primary costs involved are simply water and the energy required to generate steam, making it far cheaper than single-use chemical cartridges. However, the process is not magic. It relies on the laws of thermodynamics. Steam sterilization typically requires temperatures between 250 degrees Fahrenheit and 275 degrees Fahrenheit. Because the process utilizes saturated steam, it introduces moisture. Therefore, any device that is heat-sensitive or moisture-sensitive cannot be processed in this manner. Now that we have established what steam sterilization is, we must understand the variables that determine its success. Simply placing an item in a hot metal chamber and pressing a button does not guarantee sterility. There are critical factors that impact the sterilization process, and as a technician, you must control these variables. The first major factor is the type of microorganisms present on the device. Not all microbes are created equal. They have varying levels of resistance to destruction. Some bacteria are fragile and die easily when exposed to heat, while others are incredibly robust. In the science of sterilization, bacterial spores are considered the most resistant form of microbial life. They have a hard, protective shell that allows them to survive in extreme conditions. Because of this resistance, bacterial spores are used as the benchmark for testing the efficacy of steam sterilizers. Specifically, we use a spore called Geobacillus styrothermophilus. You must memorize this name. Geobacillus styrothermophilus is the test organism used for steam sterilizers because it is highly resistant to heat. It actually thrives in high temperatures. Therefore, the logic is simple. If our sterilization cycle is powerful enough to kill Geobacillus styrothermophilus, we can be confident that it has also killed virtually every other pathogen, including common viruses and bacteria, which are far easier to destroy. Continuing our examination of the critical factors that impact sterilization, we must look closely at the concept of bioburden. Bioburden is defined as the number of microorganisms on a contaminated device, also commonly referred to as bioload or microbial load. This is a crucial variable because sterilization is not instantaneous. There is a direct relationship between the number of microorganisms and the time required to kill them. A higher bioburden requires more exposure time to destroy. If a device is heavily contaminated, the standard cycle parameters programmed into the sterilizer may not be sufficient to kill all the organisms present. This scientific fact underscores the absolute necessity of thorough cleaning before sterilization. You cannot sterilize filth. Closely related to bioburden is the impact of soil. In this context, soil refers to organic matter such as blood, tissue, bone, or mucus left on an instrument. Soil acts as a physical shield. It protects the microorganisms buried underneath it from the sterilizing agent. Steam kills by direct contact, and if a layer of dried blood remains on a hemostat, the steam cannot touch the surface of the metal beneath that soil. Consequently, the microorganisms hiding under that soil will survive the cycle. Therefore, if an instrument is not clean, it cannot be sterile. The final physical factor we must consider is device design and packaging. Modern surgical instruments are increasingly complex, featuring narrow lumens, deep crevices, and hinged joints known as box locks. These features present significant challenges because steam must be able to navigate these complex paths to penetrate every surface. Furthermore, the packaging material itself plays a role. Whether we are using blue wrap, peel pouches, or rigid containers, the material must be breathable enough to allow steam to enter and air to exit, yet substantial enough to maintain sterility after the process is complete. Incorrect packaging, such as using a wrapper that is too tight or a container that has not been validated for steam, will prevent sterilization from occurring. Now that we understand the obstacles, let us define the requirements for success. For steam sterilization to be effective, four distinct conditions, often called critical parameters, must be met perfectly. These four conditions are contact, temperature, time, and moisture. If any single one of these parameters is missing or insufficient, sterilization will not occur. The first and most critical parameter is contact. This is the golden rule of steam sterilization. Steam must have direct contact with every surface of the item being sterilized. Any barrier that prevents this contact results in failure. We have already discussed how soil acts as a barrier, but air is also a major enemy. Air acts as an insulator, much like a blanket. If a pocket of cool air is trapped inside a canister or a lumen, it prevents the hot steam from touching the surface. If steam cannot touch the microorganism, it cannot kill it. Therefore, removing air from the chamber and the packages is a priority. The second parameter is temperature. The sterilizer chamber must reach a specific high temperature to destroy the heat-resistant bacteria and spores we discussed earlier. The standard temperature for a traditional gravity displacement cycle is 250 degrees Fahrenheit. For the more modern dynamic air removal cycles, the standard temperature is higher, typically ranging from 270 degrees Fahrenheit to 275 degrees Fahrenheit. The machine must reach and maintain this temperature throughout the entire load. The third parameter is time. The items must be held at the required temperature for a specific length of time. There is a critical inverse relationship between time and temperature that you must understand. As the temperature increases, the time required to kill microorganisms decreases. For example, a gravity cycle running at the lower temperature of 250 degrees Fahrenheit typically requires an exposure time of 30 minutes. In contrast, a dynamic air removal cycle running at the higher temperature of 270 degrees Fahrenheit typically requires an exposure time of only 4 minutes. However, it is important to note that these are standard cycles. You may encounter extended sterilization cycles, which require longer exposure times. These are typically necessary for instruments potentially contaminated with prion, such as in Creutzfeldt-Jakob disease, or when specifically required by the instrument manufacturer's instructions for use, IFU. Always check the IFU to see if an extended cycle is required. The fourth parameter is moisture and steam quality. This is often the most misunderstood factor. We do not use dry heat, we use saturated steam. Moisture catalyzes protein coagulation, which is the biological mechanism used to kill bacteria. Dry heat takes much longer to destroy life than moist heat. The ideal steam for sterilization is called saturated steam. Saturated steam is a precise mixture containing 97% to 100% steam gas and 0% to 3% liquid water. This balance is vital. If the steam is too dry, it becomes superheated and acts like hot air, which is inefficient. If it is too wet, it causes wet packs, which contaminates the load. Finally, we must clarify the role of pressure. You will often see gauges reading high pressure on the sterilizer, but it is important to remember that pressure itself does not kill bacteria. Pressure serves only one purpose in this process. It allows us to raise the temperature of the steam above the boiling point of water. Under normal atmospheric pressure, water boils at 212 degrees Fahrenheit. To reach the killing temperatures of 250 or 270 degrees Fahrenheit, we must increase the pressure inside the chamber. To effectively operate these machines and troubleshoot common errors, a sterile processing technician must understand the physical structure or anatomy of the steam sterilizer. It is not enough to simply push a button. You must know what is happening inside the metal box. The sterilizer is composed of several critical components that work in harmony to maintain the parameters of time, temperature, and pressure. The first component is the jacket. Most hospital steam sterilizers are designed with two shells. The inner shell is the chamber where you place the carts. The outer shell is called the jacket. Steam circulates in the space between these two shells to keep the chamber walls warm before and during the cycle. This is a critical design feature. By keeping the chamber walls hot, the jacket minimizes the amount of condensation that forms when hot steam enters the chamber. If the walls were cold, the steam would instantly turn into water droplets, creating wet packs. Furthermore, the jacket ensures the cycle starts with a preheated environment, which improves efficiency and reduces the total cycle time. The next component is the door and the door gasket. The door features a safety locking mechanism that prevents it from being opened while the chamber is under pressure, which is a vital safety feature for the staff. However, the integrity of the cycle relies heavily on the door gasket. This rubber seal is critical for maintaining the pressure necessary for sterilization. It must be inspected daily for signs of wear, cracks, or defects. A compromised gasket can lead to two major failures. First, it can allow steam to escape, which causes leak test failures in vacuum systems. Second, if the seal is not tight, cool air can leak in, causing cold spots and wet packs. At the very bottom of the machine lies the most critical monitoring point in the entire system, the chamber drain. You must memorize that the chamber drain is the coldest point of the sterilizer. This is based on the laws of physics. Because air is heavier than steam, cool air and liquid condensate naturally fall to the bottom of the chamber by gravity. Therefore, the drain is always the coolest part of the machine. Crucially, the sterilizer's temperature sensor, or thermometer, is located in this drain line. This sensor controls the entire process. The sterilization cycle timer does not begin until the temperature at the drain reaches the required set point, for example, 270 degrees Fahrenheit. The machine assumes that if the coldest point in the drain has reached 270 degrees, then the rest of the chamber above it is at least that hot or hotter. However, this design presents a risk. If the drain is clogged with debris like lint, tape, or hair, the air and water cannot escape. This creates an airlock at the bottom of the chamber. If the cold air cannot leave, the temperature sensor will never reach the target temperature, and the cycle will fail or abort. To prevent this, the drain screen must be removed and cleaned daily under running water to ensure a clear path for air removal. Finally, located in the drain line below the chamber is the thermostatic trap. This device acts as a smart valve. It measures the temperature of the steam and controls the flow of air and condensate. It can sense the difference between hot steam and cooler condensate or air. The trap stays open to let the cool air and water escape down the drain. It closes only when it senses that hot steam has reached it. This ensures that only saturated steam remains in the chamber to sterilize the instruments. With a firm understanding of the internal components, we can now classify steam sterilizers based on the method they use to remove air from the chamber. Air removal is the single most critical step in the process because air acts as an insulator. If cool air remains in the chamber, it prevents the steam from contacting the surface of the instrument, resulting in immediate sterilization failure. We primarily divide these machines into two categories: gravity air displacement and dynamic air removal. The first type is the gravity air displacement sterilizer, often simply called a gravity sterilizer. This system relies entirely on the passive laws of physics to remove air. The principle is simple: steam is lighter than air. In this cycle, steam enters the chamber, typically from the top or upper back, and floats above the cooler, heavier air. As the steam continues to enter, it gradually displaces the air, pushing it downward toward the chamber drain located at the bottom. It effectively squeezes the air out. Because this process relies on passive displacement rather than mechanical force, it is slower than other methods. Air pockets can be difficult to remove from porous items or complex lumens using this method. The common cycle parameters for a gravity cycle are a temperature of 250 degrees Fahrenheit with an exposure time of 30 minutes. The second type is the dynamic air removal sterilizer, also known as active air removal. Unlike gravity units, these machines use mechanical means to rapidly and forcibly remove air from the chamber before the sterilization phase begins. The most common subtype is the pre-vacuum steam sterilizer. This system utilizes a powerful vacuum pump to evacuate virtually all air from the chamber before steam is even injected. The cycle typically begins with a series of vacuum pulses, pulling air out, followed by steam injections to condition the load. This is the most efficient method for removing air pockets and allows for nearly instant steam penetration, even in porous loads. Because of this efficiency, exposure times are significantly shorter. Common standards for these cycles are 270 degrees Fahrenheit for 4 minutes, or 275 degrees Fahrenheit for 3 minutes. However, because this process relies on a vacuum system, we must verify that the vacuum is working and the chamber is airtight. To do this, a specific test called the Bowie-Dick test, or daily air removal test, must be performed every single day. This test is run as the first cycle of the day in an empty chamber to detect air leaks or inadequate air removal. It is critical to note that the Bowie-Dick test does not test for sterility. It only tests the machine's ability to remove air. If the vacuum pump fails, the steam cannot penetrate the load. This test is mandatory for dynamic air removal sterilizers but is not used for gravity sterilizers, as they do not use a vacuum pump. Another variation of dynamic air removal is the steam flush pressure pulse sterilizer, or SFPP. These units do not always use a vacuum pump in the traditional sense but instead use a repeated sequence of steam flushes and pressure pulses to purge air from the chamber. As steam enters, it pressurizes the chamber, mixing with the air, and then the pressure is rapidly relieved, carrying the air out. SFPP is classified as a dynamic process because it actively assists in air removal, operating primarily at or above atmospheric pressure. Finally, we have tabletop sterilizers. These are compact, self-contained units frequently used in dental clinics and private medical practices. While they function using the same principles of gravity or dynamic air removal, they differ in how they are supplied with water. In these units, water is often poured manually into a reservoir. Water quality is absolutely critical here. Only distilled or deionized water should be used. Using tap water will lead to mineral buildup, or scale, which can damage the chamber walls and the instruments. Regardless of whether you are operating a gravity displacement unit or a dynamic air removal unit, every steam sterilization cycle follows the same logical progression. The specific mechanics of air removal may differ, but the overall cycle consists of 4 distinct phases: conditioning, exposure, exhaust, and drying. You must be able to identify these phases on a printout or a gauge. The first phase is the conditioning phase. This is the preparation stage. The primary purpose of conditioning is to remove the air from the chamber and heat the metal mass of the load. During this phase, steam enters the chamber, and air is actively removed via the drain in gravity cycles or via the vacuum pump in dynamic cycles. As steam floods the chamber, the pressure increases, and the temperature begins to rise. It is important to realize that sterilization cannot technically begin yet. The cycle remains in the conditioning phase until all the air is removed and the full load reaches the target temperature. Once the conditioning is complete, the machine enters the second phase, the exposure phase. This is the critical killing phase. The sterilization timer starts only when the temperature at the drain sensor reaches the required set point, such as 270 degrees Fahrenheit. This is a crucial concept. If you set the timer for 4 minutes, the clock does not start ticking until the machine hits 270 degrees. During this phase, the steam holds the load at this constant temperature for the specific duration required to destroy bacterial spores. On a graph, this looks like a flat, high plateau. After the microorganisms have been destroyed, the cycle moves to the third phase, the exhaust phase. The purpose here is simple: to remove the steam and relieve the pressure inside the chamber. At the end of the exposure time, the chamber drain opens wide, and the hot steam is discharged into the drain line. The pressure inside the chamber drops rapidly until it returns to atmospheric pressure. This phase ensures it is safe to unlock the door, although you should not open it yet. The final phase is the drying phase. The purpose of this phase is to dry the packs completely to prevent recontamination. This is achieved by using the radiant heat from the hot jacket walls or by introducing filtered hot air into the chamber. This step is non-negotiable. Wet packs are considered contaminated because moisture acts as a vehicle for bacteria to wick through the packaging. Therefore, the door should not be opened until the drying phase is fully complete and the machine signals the end of the cycle. To achieve the phases we just discussed, we must strictly monitor the quality of the steam being delivered to the sterilizer. Many people assume steam is just hot water vapor, but in sterile processing, the chemistry is precise. The ideal steam used for sterilization is known as saturated steam. By definition, saturated steam contains 97% to 100% steam gas and 0% to 3% liquid water. This specific balance is critical because moisture is the catalyst that transfers heat into the bacteria to kill it. However, 2 major failures can occur regarding steam quality that every technician must be aware of: superheated steam and wet steam. The first failure is superheated steam. This occurs when the steam is too dry, meaning the humidity level drops below 97%. When steam becomes superheated, it loses its ability to transfer heat efficiently. Instead of killing microorganisms through rapid coagulation, it acts like dry hot air in an oven. It dries out the microorganism rather than destroying it. This is dangerous because the standard cycle times are based on moist heat, not dry heat, so sterilization may fail. This condition can be caused by the facility's steam supply, but also by processing linens that are dehydrated or desiccated, which absorb moisture from the steam. You can often identify superheating visually because it will char or burn paper packaging and turn autoclave tape a dark, brittle brown or black. The second failure is wet steam. This occurs when the steam contains too much liquid water, specifically more than 3%. This excess water is often caused by boiler malfunctions or uninsulated steam lines. When wet steam enters the chamber, it drenches the packs. This leads to wet packs at the end of the cycle. As we have established, a wet pack is a non-sterile pack. Therefore, maintaining the perfect balance of saturated steam is essential for the process. Once we have ensured the machine is functioning and the steam quality is correct, we must focus on the most variable part of the process, the preparation of the instruments themselves. Even the best sterilizer cannot sterilize a poorly prepared set. Proper preparation ensures that the sterilant can touch every surface of the device. The first rule is disassembly. Multi-part instruments must be disassembled according to the manufacturer's instructions for use, IFU. If a device has a removable cap or a sliding shaft, these parts must be separated. If they are left assembled, the mating surfaces where the parts touch are protected from the steam. Since steam cannot contact those surfaces, they remain non-sterile. The second rule involves instruments with ring handles, such as hemostats and needle holders. These instruments must be held in the open or unlocked position. We typically use a tool called a stringer to keep them organized and open. This is critical because the area inside the box lock or hinge is the hardest part to clean and sterilize. If the ratchet is closed, the metal surfaces are pressed tightly together, and steam cannot penetrate the lockbox. A closed instrument is a failed instrument. The third rule applies to lumens. A lumen is a hollow tube, such as a suction tip. These devices present a unique challenge because air can easily get trapped inside the tube, creating an airlock. To prevent this, lumens should be moistened with distilled water prior to sterilization, if recommended by the manufacturer. The physics here is simple. When the water inside the tube heats up, it turns into steam. This expansion forces the air out of the tube and ensures the internal surface is contacted by steam. The fourth rule concerns basin sets. When we process metal bowls or basins, we often nest them one inside the other to save space. However, this creates a problem. If two metal bowls are stacked directly together, they form a seal that steam cannot penetrate. Therefore, an absorbent wicking material, like a towel, must be placed between the layers. This towel acts as a wick, drawing the steam in between the bowls and allowing the condensate to drain out. Additionally, during preparation, you must place an internal chemical indicator inside every package. This indicator should be placed in the area of the pack that is considered the hardest for steam to reach, such as the geometric center of a dense set. This verifies that the sterilant has penetrated the packaging material. Finally, we must consider textile packs, such as surgical gowns or towels. These packs act like dense sponges. If they are too large or too tight, steam cannot pass through them. To ensure penetration, there are strict limits. Textile packs must not exceed 12 pounds in weight. Furthermore, their dimensions must not exceed 12 inches high by 12 inches wide by 20 inches long. Any pack larger or heavier than this risks having a cold spot in the center where steam never reaches. Regarding weight, there is another critical standard we must mention. For rigid container systems or wrapped instrument trays, the AAMI standard recommendation is that the total weight should not exceed 25 pounds. Keeping trays under 25 pounds is essential to allow for proper drying and to prevent ergonomic injuries to the staff. Once the packs are correctly prepared, the next critical step is loading the sterilizer. Proper loading is essential because it allows for two things: efficient air removal and free steam circulation. If the chamber is overcrowded, air cannot get out, and steam cannot get in. The first guideline applies to peel pouches. These paper plastic pouches are designed for lightweight items. They must be placed on edge, standing up, in a loading basket. You should never stack them flat on top of one another. If they are stacked flat, the plastic side of one pouch blocks the paper side of the next, preventing steam penetration. When placing them in the basket, they should be arranged paper to plastic. This ensures that the steam can enter through the paper side and air can exit. If, for some reason, a pouch must be placed flat on a shelf, which is discouraged, it must be placed with the plastic side down and the paper side up to allow air removal. The second guideline applies to solid bottom items, such as basin sets or kidney dishes. These items must be placed on their edge, tilted forward. You must never place a solid bowl flat or upside down in a way that traps water. If placed flat, the bowl acts as a cup and will hold the liquid condensate that forms during the cycle. This results in a wet pack. By tilting it on its edge, you use gravity to ensure that all water drains out freely. The third guideline addresses mixed loads, which contain both textile packs and hard metal containers. The rule here is simple: soft goods go on top, and hard goods go on the bottom. Textile packs should be placed on the top shelf. This prevents them from getting wet from condensate dripping off the metal items above. Conversely, heavy instrument sets and rigid containers should be placed on the bottom shelf. This arrangement also prevents heavy items from crushing delicate textile packs. Finally, we must consider spacing. It is tempting to stuff the sterilizer full to save time, but this is a critical error. Packs should not touch the chamber walls, as the walls can be hot enough to burn the wrapping material. Furthermore, the packs should not touch each other tightly. You should allow approximately 1 inch of space between packs. This gap allows steam to circulate freely around each item, ensuring that every package is exposed to the sterilant from all sides. After the cycle is complete and the door is opened, the process is far from over. Unloading the sterilizer is just as critical as loading it because sterility can be compromised instantly if the load is handled incorrectly while it is still cooling. The first and most important rule of unloading is the touch rule. You must not touch packs while they are hot. When the sterilizer door opens, the packs are hot and still contain a small amount of vapor. At this stage, the packaging material is vulnerable. Hot packs act exactly like sponges. If you touch a hot pack with your bare hands or even with gloves, the moisture and bacteria from your skin can be instantly absorbed through the packaging material. This phenomenon is called wicking. Wicking turns a sterile pack into a contaminated one in a fraction of a second. Therefore, you must visually inspect the load but keep your hands off. To safely process the load, you must follow a strict cooling protocol. The entire cart should be removed from the sterilizer and placed in a low-traffic area to cool. It should not be placed near air conditioning vents or cold drafts. You must never use fans to speed up the cooling process. Rapid cooling causes the remaining vapor inside the pack to turn into liquid water, resulting in condensation and wet packs. The cooling process must be slow and natural. The duration of cooling depends on the load. Generally, the load should be allowed to cool on the rack for 30 to 60 minutes. However, heavy instrument sets or complex trays may require up to 2 hours to cool completely. For older gravity displacement sterilizers, there is a specific step required before removing the cart. You should crack the door open slightly and leave the load inside the chamber for a short period to allow the initial heat and vapor to dissipate gradually before pulling the cart out into the cooler room air. Finally, you need verification. You should not guess if a pack is cool. The best practice is to use an infrared thermometer, which allows you to check the temperature without touching the item. You should confirm that the packs have reached room temperature, which is approximately 75 degrees Fahrenheit, before you handle them or place them into sterile storage. Only when the pack is cool to the touch is it safe to handle. Before you release any item for storage, there is one last non-negotiable step: checking the physical monitor. You must examine the sterilizer printout to verify that the cycle met all parameters for time, temperature, and pressure. You must sign this printout to document the cycle's success. If the physical monitor indicates that the critical parameters were not met, the load must be considered non-sterile and must be reprocessed. Despite our best efforts in preparation and cooling, technicians will occasionally encounter the most common problem in steam sterilization: the wet pack. A wet pack is defined as any package that has visible moisture, such as dampness, water droplets, or water stains, on the outside or inside after the cooling period is complete. The rule for handling this is absolute. A wet pack is considered contaminated. You must treat it exactly as if you dropped it on the floor. This is because the moisture creates a continuous liquid pathway for microorganisms to migrate from the outside environment into the sterile package. There is no shortcut here. You cannot simply dry off the pack with a towel or put it back in the sterilizer for another cycle. The item must be completely reprocessed. This means the set must be sent back to the decontamination area to be disassembled, re-cleaned, repackaged with new wrappers, and re-sterilized. To prevent this frustration, we must control the root causes. As we have discussed throughout this chapter, wet packs are usually caused by human error or steam failure. Overloading the chamber prevents drying. Placing basins flat instead of on their edge traps condensate. Using wet steam from the boiler drenches the load. Removing packs before they are cool causes condensation. And finally, a clogged chamber drain prevents water from escaping. This brings us to our final topic, cleaning and maintaining sterilizers. Routine maintenance is the only way to prevent cycle failures and equipment damage. As a technician, you are responsible for specific daily tasks. First, you must clean the chamber drain screen every single day. You must remove the screen and wash it under running water to remove lint, hair, and debris. As we learned earlier, a clogged screen traps air and condensate in the chamber, which prevents sterilization. A clean drain is the lungs of the sterilizer. Second, you must inspect the door gasket daily. Wipe it clean with a damp cloth and check for any cracks, wear, or defects. A damaged gasket causes air leaks, which will cause your vacuum cycles and Bowie-Dick tests to fail. Periodically, you should also clean the chamber walls using a non-abrasive cleaner to prevent the buildup of biofilm and mineral deposits. Never use steel wool or harsh scrubbers, as scratches on the wall can harbor bacteria. In conclusion, high-temperature sterilization is not a simple cleaning task. It is a precise science relying on physics and thermodynamics. The sterile processing technician acts as the pilot of this machine. Just as a pilot monitors altitude and speed, you must ensure that the critical parameters of time, temperature, moisture, and pressure are met for every single cycle. Success depends on your strict adherence to protocols regarding bioburden reduction, proper instrument preparation, correct loading, and controlled cooling. Patient safety begins and ends with your attention to detail. This concludes our study of Chapter 14.